bit of introduction for those who didn't follow the rest of the course. Misha gave a series of lectures on glasses, classical and quantum, and today is the last lecture, and it's going to be about quantum spin glasses. In addition to this, there's going to be a discussion of recent work that Misha did in global collaboration.
All previous lectures were about classical spin glasses, and last one, which is about quantum spin glasses, evidently I cannot present any systematic view on quantum spin glasses in one lecture, so I decided not to try to do anything systematic, but just to discuss a few examples. And first, I will briefly discuss two quantum spin glass models studied previously, and then most part of the lecture, it will be about very new results. So first, this is a most straightforward quantum generalization of Ising spin glass. The quantumness comes via transverse field, sigma x, with some coefficient gamma. Now, random couplings Jij are normalized as usual in spin glass model. So Jij square average is J squared over n, where n is number of spins. What you see on the left is a phase diagram in terms of temperature and quantum parameter gamma. At 0 gamma, it is just this usual classical spin glass. By the way, here it is, of course, the same Sherrington-Kirkpatrick type model with all-to-all interaction. But quantum generalization makes the problem considerably more complicated. What was done in this paper, Goldschmidt and Lai? They first reduced a quantum partition function by Suzuki-Trotter decomposition, which means they just take time axis, split it into many pieces, and write down this evolution between slices. So here, as k, this is index k, corresponds to time time slice number k in this sequence. Then usual Gaussian transformation is done to decouple these interactions, and here there are two types of objects. One is Q, matrix Q, which depends on replica indices alpha and alpha prime, and also it depends on time, k and k prime. Here, in this term, all these Q are off diagonal in replicas. On the contrary, another part, R, is diagonal in replicas, and also depends, yes?
In the second term in the effective Hamiltonian, so the the spin should be Sik and Sik plus 1, not Sij. Or I'm missing something? Because I don't understand the term with wise.
B over beta, sum over k, sum over I.
Yes, Sik plus 1. Yes.
Yes.
Yes, okay. It's K, it's not J, yeah.
Yes, yes. So the second term here is diagonal in replicas. And now for quantum problem, it is not trivial as it was in classical one, where it was just s squared equal 1. Here there is some non-trivial correlation function, which depends on a difference between time k and k prime. Then you have a self-consistency equation for both q and r. I will not describe any details how we did it. Just what is important here is that it is a replica symmetry breaking solution, but symmetry breaking is done in the simplest way in a one-step replica symmetry breaking. And second, and it is important, they treat self-consistently this function r as a function, as a dynamic function. It is a function of difference k minus k prime. Rather frequently in with quantum glass problems, people used what is called static approximation, which means that instead of working with time-dependent correlation function, they used some simplification just to say that this will be a constant and that's it, which is frequently not okay. And it is not self-consistent approximation here as well. So they did not use this static approximation. They treat it as a function. The cost is that nobody understands how to solve this thing analytically, so they used iterative numerical solution. And this is a result that this is a phase boundary between paramagnetic state and a glassy state. Indeed, they also checked that they should use replica symmetry breaking solution because the trivial solution also they could look for symmetric solution, but it has lower free energy, and we know that in spin glasses everything is inverted within replica trick. The more stable, the correct solution is the solution with high energy. So I think it was very important paper, and of course the lacune might be that maybe it is not enough one-step replica symmetry breaking. But to do this calculation for something more complicated like Parisi scheme, I think nobody succeeded. I'm not sure if anyone tried. In terms of just some simple physical consideration, this phase diagram is very reasonable. Just at too high quantum gamma, you have only paramagnet with fluctuations, that's it. And then this glassy phase. Good, this was one example. What happens if you...
At low temperature or zero temperature in particular, the number m is a crucial thing. We should send it.
Of course, it was not large. In their computation, it was not large. It was not large. It was like 10 maybe.
Or maybe you do not get the fine details of that.
Sure, fine details could be not correct. This is as a general picture, I think it is correct, but another quantum spin glass, possibly the simplest one. This is a quantum generalization of the random energy model. This V is a function of bit string, number of this SZ plus minus 1. And by definition, for this random energy model, energy of each such configuration is absolutely random number with Gaussian distribution. We know from the study of this original model that it has a temperature of freezing. This one. The epsilon c is the square root of logarithm of 2, such that below this temperature there is no any dynamics, just this glass freezes in the lowest energy configuration, and that's it. We are interested to study this model in presence of quantum fluctuations. The strength of these fluctuations is controlled by gamma. And this gamma is considered to be relatively small. So we are living here. If it is larger than something of order 1, then again it is purely paramagnetic solution and nothing interesting. I will show that in this region, very large part of this phase diagram is corresponds to some glassy state, which is non-ergodic, but also not localized. How we get it? First of all, let me draw you a picture. What I draw is levels of this random energy model. And this is energy. The larger is energy, the larger is density of states. At low energy, distance between levels becomes much larger. Suppose I want to consider hopping between two configurations in terms of these bit strings. Hopping occurs via this tunneling term gamma sigma x. Now there are a lot of different ways to make this hopping. The most efficient ways are, say you start from the state E naught here, and you want to travel to another state with similar energy. The most efficient way is to go up by virtual transition. Then, because here density of states is much larger, and then you travel somewhere and go back. Of course, this statement should be derived. And it can be derived just by analysis of the matrix, how matrix elements with H, A, B depend on a distance. D here is denoted as a Hamming distance between configurations. So when you increase D, matrix element decreases, but density of states grows faster. So the outcome is that this transition can be described to quite a good approximation in terms of matrix elements here, H, A, B, squared, typical average, which depends on energy. Here, epsilon is, by the way, energy divided by n. So if I want to find a matrix element from one bit string at relatively low energy to another similar one, I can do it, and I will find this exponential function. N is number of spins, and here is some function of energy normalized to gamma. This function is x squared over half at small x. So when small means that this here will be zero of energy, and I am at some negative energy. So close to main band, this function goes to zero, but at below it is it comes to logarithm 2, so it is comparable to this factor. Now,
epsilon is counted starting from a zero, which is upstairs, right? So
yes, zero. There are some levels up as well. So this is zero. Zero means the middle of many body band, and we are at some lower energies. Now, we have Gaussian distribution of matrix elements with variance which depends on this parameter energy. And also we have our original distribution of local energies of each configuration. It is this RAM. Both, by the way, average matrix element is zero. Good. Now, let me make a mapping of this system to a well-defined matrix model, which is called Rosenzweig-Porter matrix model. Why I can do it? Because I have variance of off-diagonal elements which scale as some power of the dimension of Hilbert space, gamma. And variance of diagonal elements is just one, which corresponds to this distribution. Now, what we know about such matrix model? We know that it has three different phases. If exponent gamma is less than 1, then it is ergodic. If it is larger than 2, it is a localized phase. But in between 1 and 2, it is in non-ergodic extended state, which is that was found in these two papers of Kravtsov and company, which is characterized by exponential decay of return probability with time. But the corresponding time is proportional to size of Hilbert space in some power. So it is a glass phase in a sense because relaxation is exponentially slow in the size of the system. On the other hand, it is the size of the system in some fractional power. Now, what are parameters of this mapping? The key exponent gamma which relates variance of off-diagonal elements and diagonal elements, is given by this expression. It depends on energy. And this is spacing at the energy density epsilon. So when epsilon should be smaller than square root of logarithm 2, there is some exponentially small spacing. Now with this mapping, we find how relaxation time scales with a number of spins. And also we find the scaling for Edwards-Anderson order parameter. So to the offset of relaxation function goes to some non-zero constant, and it scales also in exponential way. So there are predictions for two exponents. Theta gives us relaxation time, and eta gives us this Edwards-Anderson order parameter. Of course, this mapping was not done exactly. This mapping was done under some approximation. We can check how good it is by comparison with exact diagonalization for the same model. Here, this is a relaxation of spin correlation function, and there is some non-zero offset, and then you can find how fast it approaches. And this is for relaxation time. Finally, the result. Exponent for correlation time is, for these specific parameters, is just what we expected from our analytical theory. Second exponent is not exactly the same. It is 0.1, while from theory would tell us 0.17. So comparison is not ideal, but more or less reasonable.
I have a question about this.
Yes.
If one does different realization of the disorder, of the potential configuration, so and analyze, for instance, the variance of the exponent theta that one gets, does it match the one that one gets by analyzing different disorderization in the Rosen-Porter model? Because this is just a statement of the mean, right? I could look at the variance of these autocorrelations.
Well, a good question, but I don't know answer. We did not try to consider variance.
But for the mean, everything is very good.
Yes. Of course, it can be also studied within the same approach, but we have not done it. So, conclusions for this simplest quantum spin glass. There are three phases. Ergodic phase in this model exists only at infinite temperature. At finite temperature, it is either non-ergodic extended, or if temperature is too small, then it is just absolute glass without any dynamics. And I expect, although I don't know exact answer, that the same kind of phase diagram would work for not only for just random energy model, but also for p-spin glass, quantum p-spin glass, at least if p is sufficiently large. Because from analysis of a classical p-spin glass model, we know that difference between large and finite p and REM is very small.
Sorry.
Uh-huh.
How can you find the line of transition between the fully localized glass, the iPad glass, everything it's called, and the
This?
yeah.
It is. Yeah, I forgot to say. Look, it is our mapping here. We know that for Rosenzweig-Porter, localization comes when gamma equal 2. And so we put this equal to 2 and find epsilon as function of gamma. And epsilon is translated to temperature. Mhm. Okay, now I switch to most recent story, which is about two-dimensional XY model, quantum spin XY model on a square lattice in a random field. And main results are obtained on a Google quantum simulator. Work is done by Google Quantum Collaboration, which involves very, very large number of people. Here I just show those with whom I have more interaction regarding this work. And also I had important discussions with Vladimir Kravtsov. Let me start from some history. It is a history which is not literally related to what was done in this work, but nevertheless. As you know, the whole story about localization in many body systems, of course, it was initiated long ago by Anderson, very long ago, but major activity started after these two works about 20 years ago, where they discussed the question if it is possible that interacting disordered electronic system will become non-ergodic at some non-zero temperature. This non-zero temperature was supposed to be very low. And the basic assumptions for both these theories was that there is interaction between fermions, which is relatively weak and short range. This Altshuler, Oleiner, Basco considered some kind of bulk system like 3D, but in very strong disorder. So strong that all single particle states are localized. Another group consider one-dimensional system, but under the same conditions. The question now, was it seen experimentally? In solid-state systems, literally electronic insulators, I don't know such example. And it is not surprising because in electronic insulators, interaction is not weak and not short range. It is a strong Coulomb interaction. And there are some serious reasons to expect that the theoretical scheme which was used in these papers will not work for Coulomb interaction. But there is one very, I think, important and not very well-known paper, experimental one, which I show here. Dan Shahar group at Weizmann Institute, 2015. They studied the material which is actually a very bad superconductor without magnetic field. Amorphous indium oxide in appropriate condition prepared is a superconductor. But it can be transformed to insulating state by relatively weak magnetic field. And here you see resistance as function of temperature. Here temperature is in power minus 1/2. It at high field 12 Tesla, red, and at low field in blue. At high field with dependence is usual Efrosh-Shklovsky law, hopping conductivity. But in low magnetic field, it is something completely different. You see that it has very high curvature. The same data are replotted on the right in terms of conductivity as a function of temperature. Again, this is Efrosh-Shklovsky law. And here you see this data in blue. And black line corresponds to Arrhenius fit of part of data at high temperatures. So if it would be just activation, it go like this. But in fact, the data shows very fast decrease of conductivity in a range of 20 millikelvin. So it drops by 5 orders of magnitude. These data are consistent with the Feigel'man law, which tells us that there is some T star, and below this T star, there is no conductivity anymore. Everything is frozen. This is basically what these theory guys were predicting. Now, why, I think, why it was possible to see such a behavior in this broken superconductor? I forgot to say that here the whole idea was that suppose we switched off any coupling to phonons by some means. So the question is if electronic system itself can produce a thermal buff for itself or not. So in order to observe something like this, we need very weak coupling to phonons and also in Coulomb interaction, which is somehow suppressed. Both conditions are fulfilled in this experiment. First, electrons are bound to pairs. They are bound to pairs even here when it is insulator, when magnetic field is not very strong. When it is strong, like here, 12 Tesla, pairing is destroyed, where it is just usual electronic insulator. It behaves in a usual way. But in weak magnetic field, you destroy superconductivity, but you do not destroy pairing. So you have electrons which are bound in pairs. It means, first, that any inelastic process which involves phonons is very much suppressed because electrons interact with phonons individually, and in order to get some energy from phonon or to emit energy, you need also to do something with bound pair. And second, if long-range Coulomb interaction in this material is very weak because it has high dielectric constant of the order of 1,000. So this is to say that at least one example exists. It was not much discussed. Nobody tried to continue in this direction. I don't know why. But it is worth to remember that there is such a result.
So I have a question about this experiment.
I
have a question about
yes.
the experiment. especially a large magnetic field, I have a bit of a problem understanding that the pairs are very strong. Is there a strong spin orbit coupling playing a role? Because otherwise I would have expected something fully polarized.
Yes, in this material, spin orbit coupling is rather strong.
Okay, no, then this.
So, but still, at 12 Tesla, 12 Tesla is already sufficient to break these pairs.
Okay, it is sufficient to break.
Yes, but indeed it is strong. Otherwise, critical field would be even a few times smaller. Now closer to our main subject. Most part of activity in this direction was not about low temperature, but about infinite temperature. And the same referred to our paper, which I'm going to present. And while it seems that for one-dimensional system, it is accepted that there is a fully localized state, but in 2D or in dimensionality larger than 1, there are how to say, arguments that localized phase is unstable with respect to some thermal fluctuations, thermal bubbles. Now, what it means? Usually, at least not always, but in many cases, people consider only two phases, either ergodic or fully localized. Then, if you take this point of view, the argument about the absence of many-body localized state in high dimension tells you that you always will have ergodic phase. I think that there is a lacune in this argumentation, namely, there are more phases. As I told you 10 minutes ago on the example of quantum RAM, actually there are at least three phases: ergodic, localized, and something intermediate, which is not ergodic, but also it has some dynamics. Why? It is frequently expected that there is a direct transition from ergodic to localized, because there is example of Anderson localization, where indeed transition is a one, transition at some energy, say, mobility age. However, there is a crucial difference between Anderson localization of free particles and localization of many particle system. The difference is that for one particle in dimension d, when you increase size of system, you have power law increase of phase space, volume, L to power d. In interacting many-body system, the size of Hilbert space grows exponentially. Actually, not with L to power d here. Then, what are arguments for existence of this intermediate state in between? In matrix models like Rosenzweig-Porter and some others, there are a lot of results showing that indeed there is intermediate phase. However, these models are not directly applicable to the interacting system of interacting spins, because in this system, number of random parameters is proportional to a number of spins. So it is proportional to the volume of a system, while Hilbert phase is exponential. So in other terms, you can say that number of these random parameters scales only as a logarithm of a Hilbert space dimension. While in matrix models, it is the same order of magnitude numbers. It means that there are very strong correlations. There are random parameters, but their number is relatively small. So there are correlations, which of course are absent in matrix models or in quantum realm, which I discussed before. And these correlations can be very important. On the other hand, there is some number of works where people consider interacting systems, mainly numerically, but not only numerically, and concluded that indeed there should be something like intermediate phase. Now, closer to our experiments. It is nearly quadratic array of transmon qubits. Transmon is a just nonlinear oscillator made out of Josephson junction. Still, each of these nonlinear oscillators is considered as a spin 1/2. You can do it if you are sure that dynamics of your system involves ground state of each qubit and first excited state. Why this oscillator does not go up? Because there is a nonlinear shift. The frequency difference between 1 second and first level and zero and first and zero level, they are not equal, and this delta is large. Large in the sense that all parameters of our spin Hamiltonian, which will be used, are smaller than this nonlinear shift. Now, the advantage of this system is that it is very fast. Each experiment was done during a time of few microseconds, not larger than 3 microseconds, which is considerably smaller than coherence times. These coherence times are for the whole system, not for single qubit, but for the whole array. Then I should emphasize what is done here it is a continuous Hamiltonian dynamics. No gates, just simulation of natural quantum dynamics. And the advantage of the system is that this process, just initiation in some original state of bit string, evolution, measurement, it can be repeated many times. Many means 10 to 8. The system is sufficiently fast, so you can do many measurements.
It's the nearest neighbor.
Yes, yes. Hamiltonian is here. It is approximately square lattice with nearest neighbor interaction, XY type, plus random field along Z. Random field is in the box distribution with width W. This Hamiltonian is just the same as Hamiltonian of hardcore bosons on the same lattice, equivalent. The same system was studied numerically by large-scale quantum Monte Carlo in this work, but what we did was zero temperature limit. So it was not about many body localization, it was just about ground state properties. And they found that critical disorder is 19 in units of coupling J. So at smaller disorder, they found superfluid state. And at higher disorder, it is not superfluid, rather it is a glass. Now, what we were doing is the same model, but at infinite temperature.
Sorry, man.
Yes.
If you set J equal to
Huh?
what, I mean, you have J and V.
It is it is ratio W over J. Yes. Now, one of the main quantities which were studied here is return probability in the Gilbert space. At low disorder, like for example, 2W equal to J, you see relaxation of this return probability to nearly inverse volume of the system. Thus, it should be in an ergodic state. And also, you can study relaxation of some perturbation of density as function of time. You start from initial state, which is some, apart from random bit string, it has some amplitude of oscillation for SZ. SZ is conserved in this Hamiltonian. So this quantity cannot relax, it can only diffuse. And if you make this inhomogeneous density of SZ from along this system, you expect that amplitude of this initial wave will decrease. And it decreases. Here it is log scale, and it decreases exponentially with the rate gamma, which is some constant, and multiply q squared. Q is this here, q pi over a. This is very simple, it should be in an ergodic system. Now increase disorder. Take this W15J. Here you see that while original evolution of return probability is roughly the same, at long time it behaves completely different way. It slowly decreases, but it decreases only as a power law. And we don't have enough time to see if it will come to some something like inverse volume or not. And I will discuss these features in more details next slides. Important point is that when disorder is high, each such curve is different. You have very strong fluctuations of this return probability between realizations of disorder and between different initial conditions. Therefore, yeah?
Eta there is the power law exponent.
Yes.
And it depends on the number of spins.
Yes, I will show it in more details. It depends on disorder and on number of spins. In order to study this, you need, first of all, to make a very large number of repetitions in order to construct a distribution function of this R of t. And then you can work, for example, with typical value. I will show with this distribution function. But before, let me show you data in real space. One sort of data is just decay of local magnetization. Here, this is low disorder part, this is high disorder part. And this correlation function, which is approximately the same as imbalance, it decays as a power law, but starting from some value of disorder, it decays not to zero, but to some constant. And this constant grows with disorder. A similar feature is seen for diffusion. This is relaxation of spin density wave, which is fast and exponential at low disorder. But when you come to higher disorder, you can try to extract diffusion constant. When you see that it drops very strongly, and eventually it is not even diffusion, some relaxation of spin wave, not exponential anymore. So there is some characteristic value of disorder about 10 or 11, such that below there is a diffusion, above there is no diffusion, but there is some persistent magnetization amplitude in the long time limit. Now, in more details analysis of return probability in the glassy phase. This is an example of probability distribution, or in terms of logarithm of return probability. You see, it is rather broad. So the best thing we can do is to work with typical value of return probability, which corresponds to maximum of this curve. Here we have average logarithm of return probability as function of logarithm of time for different sizes of system. Here, disorder is 25. All of these data are from quantum simulator. Also, dots on N25 are from quantum simulator. These wiggly lines comes from numerical solution, which is available at 20 and 25. So at 25 they can cite, which is also nice. But now we see that the power law exponent, which is a slope of this straight line, it depends on number of spins and in some non-trivial way. Here it is. Exponent eta is proportional to n in power 2 plus something. This is for disorder 30. Now, another cross-section of this dependence. Let us fix number of spins and consider dependence of this exponent on disorder. In all cases, it drops with disorder rather sharply. 25, 42, 59. The largest disorder used in this simulation was 35. And it drops from 2 to something like 0.2. What happens later on, we don't know. It may go to 0, or it may decrease asymptotically to 0 with increase of disorder. Good. Anyhow, this dependence tells us that it is not localized state. There is some continuous dynamics, but it is also not ergodic phase. And it exists in a very broad range of parameters, from 11 to 35 at least. Next measure. This is about statistics of wave functions, or better to say statistics of probability distribution of psi squared. To begin with, for low disorder, you see points which are well described by Porter-Thomas distribution. It is this continuous line. Here, distribution is plotted in terms of logarithms, not p, it is p of logarithm psi squared. Next, nearly critical disorder, W8. This data for size 30 and 36, they cannot be described by Porter-Thomas, but they are rather well described by log normal distribution. And we know that log normal distribution is rather usual in mesoscopic systems, like in two-dimensional, for example, disordered electron system, log normal distribution is just universal. Good. But now when we go above critical point, 12, 15, and so on, here it was done even up to 50. Distribution is a power law. And the power depends on disorder. The larger is disorder, the smaller is this power. Asymptotically, it approaches 1. This dependence is shown on plot D for different sizes. For all the sizes, even for 70, zeta approaches 1. Now, I should say that this is not actually a statistics of eigenfunctions. We don't have eigenfunctions. What we have is a wave function which is obtained after evolution over some time. How it depends on time. Here, this data shown for J, T, 30 and 60. Solid dots for 30 and feathered dots for 60. At near critical disorder, there is some difference between these slopes of this data. Here, slope already does not depend. Here, also this data nearly coinciding. So this extra factor 2 in time does not change anything in statistics. What is the meaning of this power law in distribution function? This part, I'm especially indebted to Vladimir, who recall his old work, which never was published, but exists as archive. And in this preprint, we discussed, just ad hoc, discussed what could be the implications of a purely power law dependence of this P of psi squared. Briefly, the story is the following. If zeta is larger than 1, you can translate it to fractal dimensions dq. And the result is this. For q equal 1 and a little bit larger, dimension is 1, so like an ergodic state.
Remind us what Q is.
Q is a moment of wave function, just size to power 2q. So this is what Kravtsov called semi-fractal phase, in the sense that moments less than 1 are trivial, but starting from some q, dimensions with dq drops. So it is a non-ergodic phase, of course. Now, zeta equal 1 is a critical point in the sense that here this drop happens exactly at q equal 1 and it goes to 0. And from the data, we see that all our data are give zeta larger than 1, but approaching 1 in this very strong disorder limit. If it would be zeta less than 1, it would correspond to localized phase. But we don't see it. Additional important comment is that for this distribution, usual relation known in this multifractal theory is not valid. Okay, now I.
Why the relation is not valid?
Let's say, suppose we have power law, which just power law, which obey this relation. It would mean that zeta equal 1/2. And indeed, zeta equal 1/2 is the exponent known for the critical point for the localization problem on a random regular graph. But here we have something different. It is not described, it cannot be described by localization of a random regular graph. I will show you later another graph, another version of localization on graph model, which corresponds to our data. But before, still third measure. Apart from return probability and distribution function, this is a study of intrinsic dimension of wave function, which was done according to the method described in this paper. What we see here is that n here is number of spins or qubits. For low disorder, when we increase number of qubits, go in this way, all this data tends to 1, which is usual ergodic state. But for higher disorder, like 20 or 40, we are not going to do to 1. We show some fractional dimension. So let me summarize the major outcomes, and then I will try to present you some semi-quantitative ideas on theoretical side. So first, in a broad range of disorder, return probability decays as power law in time, and the power law is faster than square power of n, and some function of w which drops very fast when you increase W. So at large W, eta goes to 0. Then statistics of wave functions is a power law, and zeta approaches 1. Let me remind you that for 0 temperature, the critical point was found 19, which is in between our fractional phase. Now, semi-quantitative theory. First point is, let us consider a very simple model of our system, which is very well applicable at short time scales. The model is the following. Consider we have this array S here I plus 1. Let us consider links of these lattice independently from one to another. Then for each pair of sides, we can introduce some combined spin operators, tau. In terms of these operators, Hamiltonian of the link is this thing. J, tau x, flipping, epsilon, tau z.
This tau are spin 1?
Yeah, spin 1/2.
Spin 1/2.
Yes, with such definition, the algebra of this tau is also spin 1/2.
But if the two SZ are the same,
then it will be no, nothing happens.
okay.
Yes, of course, it flips only if they point in opposite direction. Clearly, this approximation may have any sense only for very large disorder, because for large disorder, majority of these random fields is very large compared to J, and so everything is just frozen. Only some small fraction of bonds exist where epsilon is comparable to J. Now, return probability for within such a model is given by this simple formula. We can calculate logarithm, average it, and it is plotted as blue broken line. Data are shown by red dots, and you see that they completely coincide up to Jt equal 1. So on short time scale, the model works very well. At long time scale, it doesn't work. It would predict oscillation around some constant. But what we see is this power law decay. Oscillations and then superimposed on a power law decay. Now, let us consider another ingredient. Here, we see noise in this system. This is not quantum simulator, but numerical calculation done for small system, 20 spins. Calculate a local spin-spin correlation function, Fourier transform it, and we find that spectrum of this noise is one wave. Now let us recall where what is known about origin of one-off wave noise in usual low temperature glasses. The picture is that let's consider, like it is usually discussed, let us consider large number of some simple oscillators, dissipative states. Each has its own rate, relaxation rate gamma, so Lorentzian function. But if the distribution function of these decay rates behaves like this, you average with this distribution and you get one-off wave noise. So the point is you need to have flat distribution for a logarithm of the rate. Now let's look if we can find something like this in our system. What was missing in this model of independent links? Evidently, missing element is interaction between this link spins tau. Apart from this sum of independent links, also there is something like that. Even when these links are far apart, there is a matrix element V, mu and nu count these links, which is non-zero due to higher order process in perturbation theory, or J over W. Each next order in perturbation theory gives you small factor. Just this ratio. Small factor is J over W, which is 1 over W. Then you have many links and many different paths to connect these links. What you get is a broad distribution of these matrix elements. So I can write matrix element like exponential of some L, and this L roughly counts the number of the order of perturbation field. But this is not yet enough. In order to get this power law decay, we need to allow for real inelastic transitions. These transitions are allowed if we have some non-zero dephasing for our spins. So the transition where one link flips and another also flips, this transition leads to the state which is not exactly of the same energy as initial, but a little bit different. It is shown by this difference. But if there is a non-zero dephasing, the rate of such process is non-zero. Dephasing rate is here. Now, the distribution of these rates R is the same as distribution of matrix elements V. It is a flat and logarithmic scale. Then the probability for each spin to flip grows with time as a logarithm of time with some prefactor. This is probability to flip for any of spins. But logarithm of return probability is a quantity which is additive of the whole system. So we need to multiply by n once again. This is how I will get n squared. How to get n in power 2.4, I don't know. The important point here is that
sorry, yeah, we are considering single flips, but we can also go and consider two Feigel'man flip.
yes, but if we, I mean, rate which I consider here is a rate of transition where two links flip together. So it is correlated process made on two links.
You know, I'm thinking something vertical before and then.
It could be something more complicated. But look, here the idea is that you definitely consider high order process as virtual process. Virtual process which gives you this matrix elements. And as a real inelastic process, it is just pairwise. Maybe there are some more complicated, of course, but at least this pairwise looks to be sufficient. Now, important point is that this superlinear n-squared dependence of the exponent proves that dephasing in this system is due to interaction, not because of bad quality of each of these qubits. If it would be a problem of each qubit, then the result would be proportional to n. Of course, I should also add that this n-squared dependence cannot be asymptotic. It is there up to this size of 70. I don't think it would be the same if we have 1,000 spins or 10,000 spins. Somewhere this superlinear dependence should cross over to linear one. But the estimate on where it should happen, I think it goes like this. So for our large disorder, it might be it is beyond the existing size of the system.
But could 2.4 instead of 2 be due to the fact that you're not really flipping pairs, but maybe clusters?
Maybe. No, not studied at all. Now, about exponent zeta, which tends to 1. This feature can be understood already in terms of this simple trivial Hamiltonian of a sum of independent links. Consider one link. When it was an initial state, say 0, probability to find it in the same state 0 and in state 1 are like this. For large disorder, almost all terms like this are very small because this epsilon is of the order of W. Now let us construct a distribution function out of these probabilities. Probability distribution, probability 4 over probability P is like this. Either it is P0 or P1. And now we calculate average distribution function by is taken into account that this P1 is always small. The result is that it can be presented in such a form, some function C of P divided by P, and this function was evaluated numerically, just this integral. It happens to be very close to 1 over P. So altogether we come to this magic exponent 1. And interaction between these links supposed to give us larger exponent. Now some remark. What means this dephasing? Dephasing for spin 1/2 is that you don't have flips, but you have fluctuation of energy of two states. These fluctuations of energies means that although energy is conserved in the whole system, but it is can somehow move from one part of the system to another. So the presence of dephasing tells us that possibly energy diffusion in this system is not frozen, although particle diffusion is frozen, as I have shown. In principle, it is possible to measure energy transport in this simulator, but it is rather complicated and it was not yet done. So we don't know experimental answer about this energy transport. Just let me mention that in solid state physics we know examples where thermal conductivity is much larger than electric conductivity. For example, granular metal, the electric conductivity is blocked by Coulomb blockade. Then you have exponentially small conductivity, but thermal conductivity in the same system is only power loss. Do we have any model, theoretical model, which can be solved and which support an idea that dephasing is stronger than relaxation? Indeed, we have such a model. It is the same, our Hamiltonian, but spins, imagine that spins are sitting on a Cayley tree. We can construct recursion relations for spin dephasing and spin relaxation in roughly in the same way as it was done for usual localization, Anderson localization by Abuchakra, Anderson, and Towers. The idea is the same, but we need to consider this gamma. Gamma is imaginary part of self-energy. So for dephasing, it is imaginary part of sigma plus minus, transfer screen function of spin. And for relaxation, it is imaginary part of self-energy for longitudinal spin component. At infinite temperature, there is a rather nice way to do it. Namely, you can rewrite Heisenberg equations for spin operators in the form which is similar to Schrödinger equation. And to do it, you need to consider extended Hilbert space defined in this way. Then you can consider Hamiltonian, also defined in this extended space. Here, bare Hamiltonian is as sigma z, and perturbation is coupling. You can derive recursion relations on a tree. left one is very much similar to the usual Abu-Chakra-Anderson towers. Now, imagine that our coupling J is too small, and the recursion like this leads to only to trivial result. So there is no gamma is 0. Is it still possible that dephasing will be non-zero? Yes, it is. To study dephasing in this situation, we need to make a Schrieffer-Wolff transformations for spin operators. And then in the next order over J, we come to this more complicated recursion. It contains coupling in higher power, but it also contains much larger number of terms. It is not a k coordination number of these three, but k squared. This recursion also can be studied by methods similar to what is known as this random polymer model of Derrida-Spohn. It's a little bit more complicated, but not much. The result is that for all branching number k, and in two different ways of approximations, we find that indeed dephasing starts at coupling which is smaller than what is needed for relaxation. So indeed, on a tree, we may have a phase where J over W is larger than this critical number, and we have interaction-induced dephasing. Then all this phenomenology which I described 10 minutes ago is valid. These calculations were done for infinite temperature. For finite or low temperature, these equations should be modified. It may lead to a different result. This is open question. To derive this equation for dephasing at finite temperature, it is more tricky. I mean, not so easy to use this extended space, but maybe it is possible. Again, this is in future. Now, about graphs. As I said already, random regular graph is not a good model for this system. But there is another model which is quite good. It was considered in the paper by Cogliandola, Tarz, Venturelli, Scherer. They studied localization, Anderson localization on a random Erdős-Rényi graph. The difference is that there are two differences. First, random graph. In a random graph, you fix only average number of nearest neighbors for each side. Contrary to random regular graph, where it is each point has definitely k connections. Here it is only fixed only in average. And second, the model which we consider does not have any on-site disorder at all. All disorder was in the distribution of hopping matrix elements between points, off-diagonal disorder. Why this model is interesting for us? Because they also study distribution function for P of psi squared. And this is one of plots from their paper. What we call beta is exactly our exponent zeta. P is an average coordination number. Increase of disorder means decrease of P. P equal 1 is a percolation threshold. So all their points show that with decrease of p, the exponent in the distribution function approaches 1, exactly like in our case. So it seems like a new universality class for this localization on these 3 structures. So I come to my conclusions. Thank you.
Thanks, Misha. So, questions? Or exhausted?
Yeah, question. The fact that the return probability distribution of the return probability is no that in the we obtained equation of which are actually the docents write Porter equations. It's only related to the fact that to that specific model, or if we add, for example, overlap interaction, we can get some similar results.
I'm afraid I missed the beginning. So
No,
Is the Porter-Thomas distribution relative only to this specific model?
no. Porter-Thomas is expected to work for any ergodic system, like random matrix theory. You have Porter-Thomas distribution. In order to have something else, you need more or less strong violation of ergodicity.
Did I translate?
So I have a question about this last part on the relation with the random regular graph. So have people studied the same problem, not on the random regular graph, but on the random geometric graph? The reason why I'm asking this is that the random regular graph doesn't have a proper well-defined connectivity, while if I have a random geometric graph, I have somehow a structure in terms of cutoff radius that gives me a sense of locality. And maybe something changes and it may be more suited to model the dynamics in this kind of.
Define, please, what is a random geometric?
A random geometric graph is a random Erdos-Schilling graph, but you only attach bonds, you only put bonds if there is a given distance between.
Okay. So this model.
Between the two nodes.
Yes. This model.
Yeah, for instance.
Yes. Yes. This model was formulated and solved to some extent by Mirlin, Fedorov, and Zomers in '92. They formulated exactly in this way, that suppose within some large radius we deal with something like random graph, and beyond there is no coupling. So this large radius was used as a kind of mean field parameter. Eventually, we reduced the problem of localization to a self-consistent equation for this Q matrix, supersymmetric method. Yes, but what was done in this work was purely saddle point approximation. Even on the level of saddle point, it is sufficiently complicated. I think nobody tried to go beyond. And interesting effects should be there, beyond saddle point. So, I mean, it is technically possible, but it is really a hard job.
Other questions? Okay, so if not, thank you, Misha. Hopefully next year we will host you again.
Okay.
Some other course. I know.